They've collected data on random samples of 50 men and 50 women. The average number of pegs the men were able to complete was 19.39 with a standard deviation of 2.52. The average number of pegs the women were able to complete was 17.91 with a standard deviation of 3.39. Does this provide evidence that there is a difference between the number of pegs men and women can compete? So question 6 asks, what is the appropriate alternative hypothesis to use for this problem? Okay, so here before we get started, let's just take a look at what type of problem we have. Here we are dealing with a numeric variable. Okay, it's the number of pegs that people can complete, and so that's a numeric variable. And we have two samples, men and women. Okay, so our null hypothesis we know is always going to be in the form of mu1 equal to mu2. That's going to be our null hypothesis. And the alternative hypothesis will be in the form mu1 either not equal, greater than, or less than. Okay, and so it says, does this provide evidence that there is a difference? So here we're going to put the difference here. Okay, so reading the different alternative hypotheses, what we're looking at is the number of pegs someone can complete. Okay, and so answer choice A says there's a difference between the number of men in our study and the number of women. That's not what we're going for. We're looking at the number of pegs that they can complete. Okay, and part B says difference between the standard deviation of pegs, and that's not what we are trying to answer here either. Okay, part C and D, or choices C and D, say the average number of pegs completed by the men in our study is different from the average number of pegs completed by the women in our study. That's also not correct, because this is talking about just the men in our study, and our conclusions aren't going to be about the ones in our study, but about the general population. So let's look at answer choice D, and that says the average number of pegs that a potential male applicant can complete is different from the average number of pegs that a potential female applicant can complete. And that is the correct answer choice, because this is about everyone in our population, which would be all potential male applicants. Okay, so number 6 is answer choice D. Okay, let's take a look at number 7 and 8, which ask for our standard error and test statistics. So just a quick formula review. For two samples numeric variables, our standard error is going to be S1 squared over N1 plus S2 squared over N2. Our test statistic T is going to be x bar 1 minus x bar 2 divided by our standard error. So for number 7, let's go through the problem and identify S1 and N1 and S2 and N2 so we can put in the formula for our standard error. Okay, so let's label sample 1 to be, just arbitrarily we're going to choose that to be men, and sample 2 we will choose to be the women. Okay, so S1 is going to be the standard deviation for the men, N1 is going to be the number of men. So let's see. The number of men is 50, and we have 50 women, so N1 is going to be 50, and the number of women, N2, is also 50. S1 is the standard deviation for men, and S2 is going to be the standard deviation for women. So let's take a look here. Average number of pegs the men were able to complete was 19.39 with a standard deviation of 2.52. So S1 is 2.52, and S2 is going to be the standard deviation for the women. So it says average number was 17.91 with a standard deviation of 3.39. So over here we're going to use 3.39. Okay, so let's plug all of that into our standard error equation. And we have 2.52 squared over 50 plus 3.39 squared over 50. Okay, so let's punch this into the calculator. 2.52 squared divided by 50, I'm typing in 500, plus 3.39 squared divided by 50. and then I'm going to take the square root of that number. So I get 0.597369. Okay, 0.597369. Okay. Now, so let's take a look at our answer choices. We're looking for something along the lines of 0.59736 or 0.5974. And we see answer choice B. So for number 7, our answer choice is B. Okay, number 8, we're going to find our test statistic. Okay, so our test statistic is going to be x bar 1 minus x bar 2. So let's go through our problem and look up what x bar 1 and x bar 2 is. X bar 1 corresponds to the mean of the sample of men. So it's going to be the average for the males in our study, the men. And reading this, the average number of pegs the men were able to complete was 19.39. So we're going to put 19.39 here. And x bar 2 is going to be the average for the women, which, reading our problem, we have 17.91. So our test statistic is 19.39 minus 17.91 divided by our standard error, 0.059736.9. Okay, so I'm going to just punch this into my calculator, and I'm going to leave the number for the standard error in there, and I'm going to do 19.39 minus 17.91, close off the parentheses and hit divide, and I'm going to hit the answer key so I don't have to retype all of this in. I hit equals and I get 2.4775. So my test statistic T is 2.4775, 29674. Let's just see what we have as our answer choices. Okay, and we indeed see 2.4775. So for number 8, our answer choice is C. Okay, let's go on. Number 9 is asking what is our p-value. Okay, so in this case, we are going to do n minus 1. Our degrees of freedom is equal to n minus 1, and so we are going to use the smaller of n1 and n2. So we use 50. Well, actually, both n1 and n2 are 50, so we're going to just have 49 degrees of freedom. Okay, we go to our table, and we see we don't have 49 degrees of freedom, so we always round down, and we're going to use 40 degrees of freedom. Okay, so looking at 40 degrees of freedom, and our test statistic being 2.4775, we're going to go to our table and see where 2.4775 fits. Okay, so 2.4775 is in between 2.423 and 2.704. So that puts us between 0.010 and 0.005. So my tail is between 0.010 and 0.005. Okay? So again, our tail is between 0.010 and 0.005. 0.005 is smaller, so it goes over here, and 0.010, or if you wrote 0.010 is greater than the tail is greater than 0.0005, that's also allowed. Okay, this is our tail area. To get our p-value, we have to double it because our alternative has a not equal sign. So when the alternative has a not equal sign, we have to double this, and so I do 2 times these numbers, and I get 0.010 over here is less than my tail. I'm sorry, not my tail, is less than my p-value, which is less than 0.020. So I multiply each of these numbers by 2. Okay, or if you do it this way, 0.010 times 2 gives us 0.020 is greater than our tail, or not our tail, our p-value, which is greater than 0.005 times 2, 0.010. So our answer choice is going to be that it's between 0.01 and 0.02, which is what we have right here. Okay, so number 9 is answer choice E. 9 is E. Okay, And let's take a look at what kind of conclusion we're going to make. So our p-value is less than 0.02 but bigger than 0.01, so something in between there. And it doesn't provide an alpha here, so we're going to assume alpha is 5%. Here we have our p-values between 1 and 2%, so our p-value is indeed less than 5%. So for number 10, we will reject the null hypothesis because our p-value is less than 5%, which is what we assume alpha to be when it is not specified in the problem. And that's how we do problems 6 through 10.